start this recording. Great. Before I forget to write the date here. It's April Fool's, guys. Did you guys see the WestJet commercial? Anyways, they're advertising the Flyer Festival. It's really funny. You guys should check it out. Anyways, you know WestJet. So, like I said, so make sure you have your chapter 7 notes. No, have an assignment 7. There you go. We'll finish the chapter 7 notes today. Kind of the biggest chunk of it is going to be just going through a big example, which I see even more assignment 7s handed in already. So you guys are figuring it out on your own. That's really good. But assignment 7 is on this regression stuff, and it's due on Wednesday. So, but like I said, you can probably figure it out, finding the line of best fit and using it essentially. And then next day we're going to do 3.4. So go back to that binomial distribution that we missed. So if you don't have those notes, I have just 3.4 and the full chapter 3 notes if you don't have them, so you can come grab them after class. If you want to read ahead, or I don't know. But we'll go through 3.4 next day. So April 1st, 2019. Yeah, so what I did is I just set up an example for us to go through. There's just the one, just because I find that this section, everyone's just kind of like, oh, that's all I need to do, that's it, right? And so we'll just go through and work through this one. All right. Let me make a blank page here. Example 4. Pull it up here so I don't have to be jumping around. So remember, just to recap, so regression, it's pretty fun stuff, right? So we're finding the line of best fit, which means we have to find the slope and the intercept of a straight line. We're given the equations, and I have to give you 5 pieces of information, right? I have to give you the standard deviation of x and y. I have to give you the means of x and y, and then the covariance, which is s subscript x, y. So you'll be given, and this is what's in the table. The x bar is 86.01. Y bar is 11.35. The standard deviation of x is 3.73. The standard deviation of y was 3.10. And the standard deviation of xy was negative 8.67. What we're talking about is, remember we were talking about the relationship between the percentage in poverty in a state, in the US of course, versus the percentage of high school graduates, right? So we've looked at, okay, so what percentage live in poverty here in the state, and what is your high school graduation percentage? And we plotted those, and we saw, okay, so we said, we've got this strong linear, right, because it looks like a straight line, and then negative relationship. Strong because we can see some sort of pattern, right? And that was kind of what we helped us distinguish between a strong and a weak relationship, right? As soon as we can see some sort of pattern, we can say it's strong or moderately strong if we want to. And so part A says find the correlation between the percentage of high school grads and percentage in poverty. So the correlation, remember, is the numerical measure of the strength and the direction of a linear relationship, right? So because we've already decided that, yeah, we have a linear relationship, we can go ahead and use the correlation. We can always calculate the correlation, but it only makes sense for a linear relationship. So given these 5 pieces of information, part A is to find the correlation. Oops. The correlation, I'll find it here. It's the S of xy over sx times sy, but I'll just find it. Where did I give it to? Here. I guess it's equation 7.1 in your notes. So we've got R is sxy over sx times sy. Oops. dy. We have those 3, right? There's no calculations there. We could use that huge formula to find, well, we could calculate the standard deviation of x, the standard deviation of y, and the covariance of x and y, but I'll just give them to you. So it'll be negative 8.67 divided by 3.73 times 3.1. Calculator here. 3.73 times 3.1, negative 8.67 divided by 11.5. Oops. Jumping around here. 563. 8.67 negative divided by that guy. I get a negative 0.749805.414. So roughly, let's just round to 2 decimal places, negative 0.75. It didn't say what to round it to, but. Our correlation, remember the properties of correlation? Correlation goes between -1 and +1, right? So you just want to check, okay, when you've calculated your correlation, it has to be between -1 and +1, right? So essentially it has to be a decimal, and then the negative or the positive is just telling you, okay, well, that's got to match the relationship on your graph, right? If you have a negative relationship, your correlation has to be negative, right? And so you just want to check in, okay, does my correlation make sense? Is it negative? Yeah, that's good. Is it between -1 and 0 because it's negative, right? Yes, it is. Is it strong? Yeah, it is, because it's larger than, or larger in magnitude than -0.5. Right, so everything's looking like we've done the right thing here. Oh, no worries. There you go. Thank you. And do you have assignment 7? Thanks. Okay, so our correlation, now we have it, now we can use it. And so part B, find the slope. So the slope from our notes, our slope is equation 7.3 So your slope is going to be B1 or B subscript 1 is the correlation R times SY over SX. It's important here that we keep track of our X's and Y's, right? On the assignment, I think I asked you, okay, which one's the explanatory variable and which one's the response variable, just to make you keep track of which one's which, right? In this case, the table tells you which one's which, right? But given a scatter plot, right, you should be able to identify, okay, well, even if I just had the scatter plot, then the percentage of high school grads is my explanatory variable. So my X, and the percentage in poverty is the response variable. So that's my Y. Because you don't want to mix these up when you're calculating the slope, especially, right? Because the slope is going to haunt you all the way through in all your calculations. And so you want to make sure that, yeah, first your correlation is good, but also that your slope looks good. So the correlation we just found was negative 0.75. And the standard deviation of Y, we're given 3.1 over the standard deviation of X, which was 3.73. Which is 3.1 divided by 3.73. For simplicity's sake, I would say if you've rounded a value in part A, you'll just use that rounded value in part B. So you don't have to carry all those decimals anymore. If you do, that's fine. I'll know what you're doing, but you don't have to. So we've got negative 0.75 times 0.831099196. So I get negative 0.623324,397. So roughly negative 0.63. Just because. Go to 3 decimal places. Yeah. So now we've got a slope. Again, our slope is negative. Right? And if you think about the slope should be the rise over run. So you can kind of double check on your graph if you have one. But otherwise, you can just trust it. Okay. Part C. Interpret the slope. This just means taking the definition of the slope and applying it to this problem, right? So the definition of the slope is for each unit increase in X, we'll see a slope increase in the predicted value of Y. Okay. So in terms of this problem, we'll say for each unit increase in X, which is the percentage of high school grads, in percentage of high school grads, I'll put in brackets X, just in general. We will see a negative 0.623 increase, or after that, I'll say slope in brackets. Right, whatever the slope is, increase. Here's where I don't know, I like to have just the same blurb over and over again so I don't get confused. And so I'll always just say, even if the slope is negative in this, like in this case, I'll still say a negative 0.623 increase, right? That's the same as a 0.623 decrease, right? But then you have to drop the negative and throw in the decrease and kind of make that switcheroo. And so I'm not going to bother doing that. You're welcome to do that. But I'm just going to say it's a negative increase or it's a positive increase and thus a real increase, right? But you're not wrong if you just say it's a negative 0.623 increase. In the predicted value of percentage in poverty, which in general is your Y. So I'm just plugging in my values into the definition of the slope. Okay. Any questions so far? Pretty good. So D then is find the intercept. I can only assume it's equation 7.4. It is. So we've got B sub 0 is Y bar minus the slope that you just found. So you can see how it would haunt you all the way through. But like I said, if on the test, or I guess it's the final now, or even on the assignment, if you found the wrong, it could even stem back to the correlation, right? If you found the wrong correlation, but you used it correctly all the way through, then you're not going to lose that many marks, right? I'll take marks off for not finding the correlation correctly. But then if you just use it the way you should be using it all the way through, then you won't lose any more marks. Yeah. So consistency is going to be really important. Just don't doubt yourself. If you found the correlation and you've checked it and it looks good, then just keep using it and stick to your guns, basically. So we find the intercept using Y bar and X bar because of that fun fact where the least squares regression line will always pass through X bar, Y bar as a single point. I think that's kind of cool. So we know Y bar was way up here, 11.35, and X bar is 8601. 11.35 minus the slope, which is negative 0.623 times X bar, which was 86.01. Negative 0.623 times 86.01. We get 11.35 minus negative 53.58423. Mm-hmm. 11.35 minus the negative number is essentially adding them. So 64.93423. What do you guys got? Okay. Just double checking I got the same numbers. All right, so now we know the intercept. The intercept is where the line is going to cross the y-axis, right, which is where x is 0. And so in part E, interpret the intercept we apply the definition of the intercept to the value that we just found. So the intercept, right, is the predicted value of y when x is 0. So it's the predicted percentage in poverty, which in general is your y. That's the predicted value of y. When the percentage of high school grads which is your x, is 0. I'm going to throw on an additional little side question here. Interpret the intercept, and then is it meaningful? Just because I don't seem to have it on here. When we ask if it's meaningful, right, what we're really asking is whether x will ever be 0, right? Do we even care about the predicted value of y when x is 0? A lot of the times we don't, right? It's just a point where the line is going to cross the y-axis, right? But no data is ever going to be around the y-axis. And so then it's not meaningful. So in this case, what we would do is we would just say, okay, well, our data here, percentage of high school grads at the lowest point is around, I don't know, 70, 75-ish, right? And so is it ever going to be 0? No, unlikely. Even knowing nothing about data, especially when we know something about like the percentage of grad rate, well, no, we're never going to have a stage where no one, absolutely no one is graduating high school, assuming high school is still a thing, right? That's never going to happen. And so here our data is between, let's call it 70 and 95-ish, right? And so it's a long ways from 0. And so, no, the intercept's not meaningful. It's just going to be where the line of best fit, right? If we just kept going and going and going until x is 0, that's where it would cross the y-axis, right? So it's not meaningful, but we can still find it and we still need it. So I'll say something like this. Since percentage of high school grad will never be 0, the intercept is not meaningful. Last day we called, so when we're using values outside the range of x that we have in our data, right, to predict new values, then we're extrapolating, right? So in this case, our intercept is an extrapolation. But we'll talk more about extrapolation, I think, in part I or somewhere. Yeah. So F, find the least squares regression line of percentage in poverty as a function of percentage of high school grads. So what we're doing is we're just finding y hat is b0 plus b1 x. That's your least squares regression line. Essentially y equals mx plus b, right? Just different coefficients. Instead of m, I've got b1. Instead of b, I've got b sub 0. Kind of switch the order, but our y hat just stays y hat and our x just stays x. Remember, y hat is the predicted value of y. And so b sub 0, we just found it 64.93 plus b1, which was negative 0.623, I want to say, or 32. 23. times x. Which we want to write it a little cleaner, then we can go y hat is 64.93 minus 0.623 x. If you want, and if it makes sense to you, then what we could write, well, y is the percentage of in poverty. If we put a hat on that, makes it the predicted percentage in poverty. Is 64.93 minus 0.623 times x, which in this case is the percentage of high school grads. So if that makes more sense to you to read it that way, then you're welcome to write it that way. I'll just stick to x and y just because it's, I don't know, it's quicker to write, right? But because the whole goal of building this line is to be able to plug in some percentage of high school grads to get some predicted percentage in poverty, right? It might be helpful to just put in the variables, right? Percentage of high school grads, percentage in poverty. And then it's kind of a no-brainer when in part H, you have to predict the percentage in poverty of a state with an 80% high school graduation rate, right? So we're going to use this line to predict new values of y. But first, I've got a little side step. Part G, draw the least squares regression line on the scatter plot below. This is really just to prepare you for the final. I'm going to see if I can drop this one. I don't think it's really that important for you to know how to draw a straight line. I think it's kind of silly, but as it stands right now, it is on the final, so figured I better show you how to draw a straight line. So here we go. Let me just grab this. You guys have the graph, but I'll just grab it, pull it down here. Oh. Oof, nice and big. So this is part G. Draw the regression line. To draw a straight line, right, all you need is 2 points on the line, right? So what you're gonna do, I'll use a different color here, is you're gonna plug in some percentage of high school grad, right? Preferably one that you can see easily on the graph, right? So I would use 80, 85, or 90, right? Because then you can just trace up. So you're going to pick one of these x values, or two actually, right? One for the first point, one for the second point. They can be as close or as far away as you want from each other, right? But you're just going to pick an x value, plug it in, find the value of y, and then try to figure out, okay, well, if I use 80 here, then my predicted value of y might be here, so then I have to kind of guesstimate where it would be on the y-axis. And so what we would do is we would say, okay, well, find 2 points on the line. By picking 2 values of x. Of course, if x equals 0 is on your graph, that's a good one to pick, right? Less math, but. So what I do is I just kind of make a little table here. So I've got x and y coordinates. Y is 64.93, I want to say. Yeah. Minus 0.623 times x. So y hat. So like I said, I'm going to use, I don't know, 85 and 90. So I've got my two values of X here. I'm going to find the values of Y. So Y hat is going to be 64.93 minus 0.623 times 85 for the first point. I get a predicted value of 11.975. If someone got something else, okay, let me know. And then we do the same thing for the next point, 64.93 minus 0.623 times 90. So times 90, and then 64.93 minus that, I get 8.86. So when X is 85, we get a predicted value of Y of 11.975. So 85, I can just kind of draw a fake grid here. And 11.975 is going to be pretty close to 12. I'll just put it right below it. So this is my first point, which is at 85, 11.975. Obviously, it's not going to be a very good graph because I'm just eyeballing it here. My lines aren't that straight, but it's the idea of finding predicted values of Y at some values of X and then being able to plot those points and then connect those points. So what was our next point? When X is 90, Y hat is 8.86. So 90, I can do the same thing. And 8.86, I'll just put it kind of there. So at 90 and 8.86. Do little orange circles around the ones I've found, otherwise they kind of blend in. So all you need to draw a straight line, right, is 2 points on the graph, and then you just need a straight edge. You can use your, I don't know, your formula sheet booklet or whatever you have handy, even just folding the page over, and then you connect the dots. Oops. Right. So you're connecting the dots with your paper, and then remember, a straight line just keeps going and going and going, and so you can just connect the dots and then extend the line, and then you've drawn the line of best fit. Now it's a little jumpy on the iPad here, so I'll give it a go. Did it draw? It did. Didn't really go through the point, but you win some, you lose some. Good enough. So this is Y hat is 64.93 minus 0.623x. You don't have to put that on there, but just to highlight what we just did. Okay. Any questions about that? It's kind of remaining from whatever math prereq course you had to take before you took this, probably. All right. So, what's the next point? Oh yeah, the reason I didn't pick 80 was because we use 80 later on. let's see here. H. So now we're going to predict the percentage in poverty of a state with a 80% high school grad rate. So let X be 80. And the reason that we're using just flat 80 and not converting it to a decimal, right, is because you're going to look at the scale of your graph. And if the scale of your graph is in a percentage, right, 80, 85, 90, you don't want to be plugging in 0.8, right, that would put you way over here, right? So you want to match whatever the graph is giving you, right? Or whatever the data is giving you, even looking at the initial data, if that's all you have, the average of your x's was 86.01, right? So then using an x of 0.8 wouldn't really make sense, right? It's not going to match the data you've been given. And so you want to make sure, okay, well, if we're talking percentages, then you have to match whatever the data is giving you. So if we let x be 80, we have to find y hat, the predicted value of y. Same thing we just did, right? Just with x equal to 80, 64.93 minus 0.623 times 80. 0.623 times 80, 64.93 minus that, I get 15.09. Now you can just double check on your graph, right, if that makes sense. My line didn't go that far, but 80, and then going up to the line, yeah, 15 point whatever looks reasonable. That's not how you're going to predict it, right? By using the line, you're going to use the equation, but you can use the line to check it. HI. You don't have to say anything. You can just do the calculation and then move on. If you want to say something, that's fine, but you don't have to. So part I, predict the percentage in poverty of a state with an 50% high school grad rate. Do you trust this prediction? So we can go ahead and let x equal 50. Find y hat, 64.93 minus 0.623 times, 50. I get 33.78. Looking at our data, right, we have to be careful because this line is only built off of data. Like these points, right, are all our data points, right? So this line is only built off of data between x equals 70-ish to 95-ish, right? So we should only be using this line to predict values inside the range of these x's. Lines just keep going forever and ever and ever, so we definitely can use them. But our estimates are less reliable, right, because we're extrapolating. And so an x of 50 is outside the range of our data. So then when I ask you, do you trust this prediction? No, because we're extrapolating beyond the range of the data. So here, do you trust this prediction? No. Since x equal to 50 is beyond the range of the data, we are extrapolating making our estimate or our prediction less reliable. Questions? Then finally, for part J, we're asked what percentage of variability in the percentage of in poverty is explained by the least squares regression line on percentage of high school grads. So here I said, well, as soon as you see percentage of variability, right, whether I'm giving you the percentage of variability or I'm asking for it, what percentage of variability, as soon as you see percentage of variability, it's R squared, right? So R squared we use as a measure of goodness of fit. How well does our model predict new values of Y, right? So R squared goes between 0 and 1, so it's a percentage. And so basically find R squared, right? It's asking what percentage of variability in Y is explained by the least squares regression line on X. That's the definition of R squared. And so R squared is just the correlation squared, which was negative 0.75 squared. So 0.5625. Or if you want, 56.25%. If you're looking at the extra practice problems that I've posted on Moodle, right, then you'll see some questions where I ask, okay, where I give you, so the percent, so 60% of the variability in Y is explained by the least squares regression line on X, find the correlation, right? Then you could just take the square root of it, right, to get back to the correlation. But because R squared is always positive, right, it's between 0 and 1, you'll have to add on the negative to the correlation if you have a negative relationship. So if you're trying those problems, then that's what you would have to do. Okay. So what this is saying is that, okay, well, the percentage of high school grads is capturing basically 56% of the activity and the percentage in poverty, meaning little less than half of all that activity is not captured by the percentage of high school grads. So there are other things that are influencing the percentage in poverty. But percentage high school grad is a pretty good predictor of percentage in poverty. Yes? As soon as you can see some sort of pattern, like here, we kind of looked at this and saw, yeah, there's some sort of pattern, you can go ahead and say it's strong. Right, so if it's just random scatter around whatever, nowhere, right, just kind of random scatter, then you have a weak relationship. But for us, as long as we see some sort of pattern, it's strong or moderately strong. If you don't feel comfortable calling it strong, you can say moderately strong. But also, you can look, if you have the correlation, and the correlation is bigger than 0.5 on either end-ish, then it's strong. Okay, yeah, any other questions? Good. Okay. So, we did R squared. So just briefly, we'll talk about assessing the fit of a line. So if we built a model, then we should check it to make sure that it's good, right? And so what usually ends up happening is I've got, and you've seen it in the lab, right? I built mod 1, and then mod 2, and then mod 3, mod 4, mod 5, and they're just variations of each other where I change little things as I go, and then I'll do, for the best ones, I'll do a little analysis on the goodness of fit. So assessing the fit of a line. So first, we spent a lot of time, okay, is this a linear relationship? And yeah, of course, there's hypothesis testing that you could do to see if you have a linear relationship. We don't go that far, but there's all these little venues that you can go down, right? You can test if your slope is significantly different from 0, right? That would be a hypothesis test. You can test your intercept, although that's not that interesting. You can test your correlation. Is that significantly different from 0, right? Or significantly different from some value, right? So you can do hypothesis testing around all of these things that we're not going to do, but just be aware that you can. So R squared is kind of the most common thing that we use to say, okay, I have a really high R squared, so my model is really good and gives reliable estimates, or at least I think that it does based on my data. You'll also want to do a residual analysis. So what that means is you want to collect all your residuals, and in R, when you do generate a linear model, right, use that LM command, it generates the residuals alongside it. So we didn't do that, but they would just be there hiding in the background. Otherwise, what would you have to do? You would have to take all the points, right? All these XY coordinates, for each value of X, you would have to calculate the predicted value of Y, right? Because the residual is the distance between the predicted value and the actual value, right? And then you would have to calculate the difference. That's a lot of work, and so we're not doing that. But assuming that you have residuals to work with, right, which is easy in R, we used to make people do it by hand. We don't do that anymore. I'm glad. It's really silly. But so what we can do is we can use the residuals to double check that we have a linear relationship, right? So check for linearity. We also want to have nearly normal residuals, right? So if we make a histogram of our residuals, they should follow a normal distribution, right? Essentially, half of them are close to the line, and then very few of them are far away from the line on the lower end, and then same thing, very few are far away on the upper end, right? But most of them are hovering around the predicted line. And we're also looking for constant variability. So constant variability is when we have something like, I don't think I have, here's our line, I'll start there. So if we have constant variability, then we've got this kind of scatter like this. If we have non-constant variability, then we have something like this, right? Where for this part of the data, right, the line is doing a really, really good job. So for this chunk, we've got reliable estimates, everything's going well, but then something happens. So if we try to use the same line for values of X that are out further out here, then we've got more or less reliable estimates, right? Because we've got more variability. And so we want to make sure that, yeah, this line has constant variability around it, right? So that there's kind of an even strip around it, just to make sure that the line does as good a job for all values of X. So that's what it's hinting at. So of course, just talking about these conditions that we would check with our residual analysis that we're not going to do, but just kind of talk about it. Right, we have to make sure we have a linear relationship. Everything kind of hinges on that. We've just made a straight line, so make sure it's linear. And then we make the residual plot. So down here, these guys are the actual relationships. And the ones below it, because it's not clear, are the residual plots. So a residual plot is just going to be your residual on the y-axis as the response, and the explanatory variable on the x-axis. Okay. Residuals should be centered on 0. Right? You've got some points below, some points above, right? But residuals should be centered on 0, and we're looking for random scatter around 0. What happens is that the residual plot here, if this is your actual relationship, right, it looks linear, that's good. We've got constant variability, that's good. And it also looks like we're going to have nearly normal residuals. And so that's just reflected in the residual plots, right? We've got random scatter around 0. And then the residual plot just helps us magnify the relationship essentially. So here, it looks like we've got this kind of curved relationship around the straight line. Right? And then when we look at the residual plot, it just kind of magnifies that. Right? That we've got this, no, we've got this curve here, so we probably shouldn't be fitting a straight line. And then same here, we've got this non-constant variability-ish. I personally wouldn't be too concerned if I saw something like that. It's just kind of a weak relationship, but it's supposed to show non-constant variability. Which again, it's a little bit amplified in the residual plot, right? But not, I wouldn't say too clearly. All right. Residual plots. So then you want to make sure that you have nearly normal residuals, so they follow a normal distribution centered on 0, right? You just want to have some of them below, some of them above, most of them close to the line, right? Making for a residual of 0. And so we can use the methods that we learned before, right? We can make a histogram, or we can make a QQ plot of the residuals. The QQ plot, it just plots the theoretical against the actual residuals. If it follows a straight line on the diagonal, then you have a normal distribution. And then we talked about constant variability already. It's also called homoscedasticity. Hard to say. But anyways. Okay. Any questions about residual plots? Oh. Then let's talk just briefly about outliers. So outliers are cases when we have things like this in our scatter plot, right? So here we've got most of our data kind of hanging out in the lower right-hand corner, but then we've got these 4 points mainly, right? This one's a little bit of a concern because it's a little bit far out, but because it follows the general trend, I'm not too worried about it. But these guys, right, are going to affect my relationship. So, which is pretty obvious when we try to fit the line. So what we did was, okay, well, we fit the line with the outliers, and it gives this dotted line. And so this dotted line, yeah, it's trying to pick up these guys, these 4 points over here, these outliers, but it's really not doing, well, it's not even doing a good job of capturing those outliers, right? It's predicting below, but also now it's definitely not doing a good job of capturing the rest of the data, right? So when we keep those outliers in there, it's not doing a good job overall. So what we would do is we would remove those outliers, we would look at the line and say, okay, well, I'm going to use that line and probably try to use some other model to try to figure out how to model these guys separately. And so outliers are a little bit tricky because most people, once you've collected your data, will look and say, oh, there's this huge value. No, I'm going to delete that row. I don't need it, right? But what you should be doing is you should keep all your data, unless it's clearly a data entry error, right? Then you can't keep it. But if it is legitimate data, like in this case, it does happen that you have these outliers, right? These rare cases, then you need to know what to do with them, right? And so what we do is, well, it's just that. So you do the line, or you find the line with all the outliers, so with all your data points. And then usually what I do is I slowly remove data points to see if there's a huge change. Right? As soon as there's a huge change, like going from with outliers to no outliers in this case, right? And I look at this and I say, well, this one's obviously doing a way better job of capturing a lot more of the activity. So I'm going to use that as my model, right? I wouldn't use this green one, but I always kind of try to keep as many outliers as I can in my data, right? If it's not making a huge difference in my model, then I may as well keep all that data, right? So what you want to do is you want to see if a point is influential or not, right? So if it's influential, then yeah. No. Like in this class, we're not even gonna do anything. We're just gonna talk about this. Yeah. But yeah, so for us, as far as we go, we'll say, okay, we'll fit the line with all the data points. And then we'll take out the outliers, or the ones that we think are outliers, fit the line again, and then you pick the one that looks the best, right? Look at the R squared, look at the residual plots, and then if your outlier or outliers are non-influential, then I would argue just to keep them, right? We're always kind of trying to keep as much data as we can. So if it's not changing your line, right, or even changing your R squared by that much, then why not just keep them? And so we've got these influential outliers, high leverage points, low leverage points. But usually we just end up looking at, well, the actual line on your graph, but also your R squared typically. And then if you have to drill it down, then you can do the residual analysis. Oh. Lurking variables are things that you have to keep in mind. So if you've plotted the relationship between two variables, right, and you see the strong relationship, and we kind of talked about it before, right, where two things are so obviously related to each other, right, but they're not necessarily one's not causing a change in the other, right? They're just related to each other, but also lurking variables. There's other factors that we haven't taken into account, right? So we said our R squared for our model for the percentage in poverty and the percentage of high school grads was 56%. And so almost, well, less than half of the variability that we're seeing in the percentage of poverty is not captured by the percentage of high school grads. So there are other variables that we haven't taken into account, right? So then we can have these lurking variables, and I just think this one's so cute. I wish they didn't turn on that seatbelt sign so much. Every time they do, it gets bumpy, right? That's true. Right? As soon as the seatbelt sign comes on, you know it's going to get bumpy. But that's not why, right? There is a relationship, absolutely. And it's a very strong, probably linear relationship, right? But there's other things underlying there. Okay. Any questions? Oh. So make sure you do assignment 7. And then if you don't have the chapter 3 notes or the 3.4 notes, then you can come grab them. Otherwise, I don't know, I got nothing. You can work on your assignment 7 if you want. But I know there's a law exam coming up, so I'll see you guys on Wednesday.